All right, thanks again. So we are starting off with CFT on Taurus. And um, to give this some perspective, what we were trying to say is that suppose you have something like, so let's say you have lambda phi 4 theory, okay? So there you have interactions that look like this, right? So you have things which go in. So yeah, I mean, depending on how you want to actually do this, you can have things going. And so let me not put arrows, but you know what I mean. So these are point-like objects, and so field theory is based on these point-like objects, right? Suppose you have a similar thing for strings, okay? So what would you have? You would have one string going in, something happening here, then another string going in, and something else going out, right? So this is going to be something like this. So I've just fattened this whole graph out, okay? Now see that so these are closed strings, okay? Closed strings. Now, I agree that this looks horrible, but you know what I mean. So let me be a little bit more careful and try to draw this. So this and this and so on and so forth, okay? So I just fattened this whole thing out. Now you see that you can sort of deform this, right? You can deform this, and topologically, this will be the same as a sphere, but there'll be four sort of punctures on the sphere, okay? Where you have actually inserted something. So these I mean, insertions, this is something that we didn't do that much. These guys that I'm trying to point out here, these are what are called vertex operators, and these are inserted. You'd remember that there are these things that you found out the weights of, right? E to the I k x, where x was your was your scalar field, k was your k was your sort of momentum, if you wish. You found out the weights of these guys, and you found that these are primaries, right? And so what happens is, when you're looking at scattering amplitudes of strings, you actually insert these sort of operators here, on a sphere. So if this is a 4-point, if it's a 4-point amplitude, so these are four sort of mark points where you have inserted inserted vertex operators. If it's something like a 6-point amplitude, obviously things will get harder to draw, but okay, that and that and that and that and that and that. So if it's something like this, then this equivalent thing is going to look like a sphere, but you have 6 mark points now. Okay. And you insert these operators out here. For your endpoint amplitudes, so on a sphere, you have to insert these n sort of vertex operators, or n operators, if you wish. So why these are vertex operators is something that we can speak about later. But it's sort of it's a sphere where you have put in n of n such operators. So that is what happens when you're looking at tree amplitudes. Okay, if you're looking at tree diagrams, so these are what are going to happen. But string theory, or any such thing, it will so for example, you can think of field theory amplitude that looks like this, right? So this is a phi, well, it's a phi cube theory here, but okay, something like this. Okay, you can think of this, or So this, for example, will sort of fatten out to something like this, which is fine. This is also okay. But then there is something like, something happening which is like this. Okay, so I'm out of space. So let me try and make this a little smaller or move this around. Let's move this around and make this smaller as well. Starting to look horrible, but you get what I'm trying to get at, right? So this, so when you're trying to deform something like, so if you want to find out what the equivalent of this is, you figure out very fast that what you want is no longer something that you can draw on a sphere, right? You have to actually get something with a hole in it. So this is something, and then you can put these extra things out here, these extra insertions. And as you go on and on, if you want something like an equivalent of a two loop amplitude, then this has to be, then the string theory equivalent will be something like this, where you have two of these guys here, and you have to insert two guys here and two guys somewhere else. So as you can see that if you are approaching it, approaching the study of CFTs from the point of view of string theory, it's apparent that you need to actually try not only to look at the plane, if you wish, which is equivalent to the Riemann sphere, but you also have to do better. You have to try and figure out how to understand CFTs on things like things with one hole, things with two holes, things with n number of holes. Okay. So the genus of these surfaces, so you will have to figure out how to define CFTs on arbitrary genus Riemann surfaces. We will not be going into that much of detail about the higher ones, but we will in this this part of the course be interested in the things with one hole, or what is called the CFT on a T2. So that's what I've been trying to write down here. So you see that if you are looking at a tree diagram like this, that is equivalent to having four of these sort of identity mark point on a sphere. And so for loop diagrams, one needs to go higher. And so, for example, if you're looking at one loop amplitude, so you have to consider CFTs on a torus, like I've just shown you. Okay, very good. You will also see that in order to naturally define partition functions of a CFT, we will have to go here. That's what we will learn next. All right. Okay, before we do that, let me just get rid of this. Sorry. Get rid of this. All right, very good. All right, so now that you have we have motivated why you want to look beyond the plane. Let's try and understand what do you do in order to get to this donut shaped object. Remember, so if you have, well, I don't have, I do have something here. Let's see. All right, this is some paper of. So you remember, if you had a plane, then what you could have done is you could have identified these two ends of the plane, and what you got at the end of the day was a cylinder, right? Now, what you are going to do, unfortunately, I'm not going to be able to do it that well. Let me try the other way around. Okay, here. Now, what is the best way to form this torus? That is, if you take this, and now if I can identify its two ends, which is going to be very difficult, but you know, think about it. So this, if it had been blown out in the right way, then this would have been what you wanted. My paper is all crumpled, but that's what you want to do. So in order to get to this shape, this donut shape, so first you form a cylinder, and then you identify the ends of the cylinder. Okay. Remember that the cylinder end that you need to identify have to so you know the mapping that you have from the from the plane to the plane to the cylinder. Suppose you look at a finite section of that and you identify its ends, then you have got what you wanted. So that's what we will do. And you remember that the map for the from the plane to the cylinder was given by this equation 6.1, where z was the coordinates on the plane and omega is x naught plus ix1. These are the coordinates on this cylinder. As I say here, the simplest way to move to this torus is to cut out a finite piece of the infinite cylinder and identify its boundaries. Let's go a little further. Again, this is something you'd remember. A primary field on the plane will transform to this cylinder as the following. So here these are weights h and h bar, and so so cylinder is related to the things on the plane by this factor of z to the h and z bar to the h bar. If you were to look at only the chiral sector and not speak about the antichiral one, we will do this later. But notice that the cylinder, then can be more expanded in this form. So you have a z to the h in front, and you have phi n z to the n minus h out here. So you see that this h and this h goes off, and what you are left with, if you re-expand this in terms of the modes on this cylinder, then this is just phi n e to the n omega. You can do this not only for primary fields, but you can also do it for the energy momentum tensor. And then what you have to do is you have to make, you will have this piece which is the transformation piece. If there were no central term, it would behave like a primary of weight 2. So that is why you have this squared out here. And you also have the Schwarzian piece, which is the reason why T is not a primary field. And once you do this, and this is something that you have done in the past, you would see that the answer, this Schwarzian is just minus a half, and then you will get that the cylinder energy momentum tensor is related to the plane like this. What we want is also to relate the modes of the energy momentum tensor on the cylinder to the modes on the plane. And then what you see is the following: that you do this, you see that the you can expand this out, and then what happens is that you just make this into ln z to the rn. But there is also this central term piece which you have. So now what is going to happen is that if you expand it in modes, then it is going to have this ln piece, but there is going to be a delta n0 piece. So all the ln's are fine, except for L0, which has a shift. So from the cylinder to the plane, if you are looking at all the other ln's, these are the same. But if you're looking at L0 is shifted by the central term. Okay, so there's a similar thing for the L0 bar as well, which is related by C bar. This is important. This is important when we will go forward. Let's keep this in mind. This plays a crucial role later on. Okay. So that's what you need to remember. All right. Now let's try and focus on what we want to do today. So the modular group on the torus is what we want to now address. As we said, to arrive at the torus, we need to identify the ends of the cylinder. So now remember that not only is space periodic, but the temporal direction is periodic as well. And there's one last thing that you need to remember. I don't know how much of this we'll look at the end of the day, but you need to remember that just identifying, instead of just identifying the ends, what we could have done is what we also could have twisted it and then identified it. Okay, so this is going to be related to something maybe which we can address near the end of the course, but just keep this thing in mind as well. Okay. All right, now let's formalize this process of identification, and let's do this in the following way. So there is this lattice on the plane. So what we're going to do is that we're going to identify so we're going to create this lattice on the plane. Okay, so we're going to identify points points in C such that this omega is identified with M alpha 1 and N alpha 2, where M and N are things take integer values. So you just mark these things out. Okay, so that's the way that you're going to create this create this sort of lattice. Alpha 1 and alpha 2 are complex numbers. So this pair is going to span a lattice, and this the smallest cell of this is going to be the one that I'm trying to shade here. So this guy is going to be called the fundamental domain of our T2. So the fundamental domain of the torus is going to be this particular cell, or this one if you want. Okay, anyway, so so we obtain the torus by identifying the opposite edges. So you identify this edge with this edge, and you identify this edge with this edge. Okay, so that is what you do. So this with this and this with this. Okay, so if you do that, then you have folded it up and you get what you want. So the quantity that describes the shape of the torus is called the complex structure, or the modular parameter. This is given by tau. So I should have put an equation here, number, which I have not done. But anyway, so this is alpha 2 by alpha 1, which is tau 1 minus I tau 2. This is going to be important. Okay. Now what is going to happen is that different choices of alpha 1 and alpha 2 will give you the same lattice, and hence the same particular, but same T2. Hence, so let's try and see this. So let's let alpha 1 and alpha 2 and beta 1 and beta 2 describe the same lattice. So if that is the case, they're going to be related by some matrix which has integral entries. And by the same way, alpha 1, alpha 2 should also be expressible in terms of beta 1, beta 2. If we do this, then we find that this is this is just the inverse of this guy. If we require that the inverse matrix also has integer entries, then what we see is that AD minus BC has to be plus minus 1. This means that what this entails is that every unit cell is going to have the same same volume at the end of the day. Okay, so the lattice, so another thing that is that should be clear from here is that if you have a lattice which is spanned by alpha 1 and alpha 2, a lattice which is spanned by minus alpha 1 and minus alpha 2 will be the same, right? So if that is the case, then we see that I mean we can mod out by this by Z2 action. So that just means that I mean we could have this matrix with minuses as well. Okay, so those two amount to the same thing. So I mean so alpha 1 and alpha 2 and beta 1 and beta 2 are going to be related by I mean SL2Z modded by Z2 transformations. Okay, that's what we are so that's what it is. And finally, if you choose alpha 1 alpha 2 as 1 and tau, remember what this is, tau was just alpha 2 by alpha 1. So we're just sort of there is a scale in the system which we have just we have just scaled things out in some sense. So if we choose alpha 1 as 1, then alpha 2 just becomes I mean tau. And then what we have is that the modular group of the torus is an isometric group acting on this modular parameter tau, but as tau goes to a tau plus b by c tau plus d. Okay, where this I mean a b c d take values in. So this particular thing will be a matrix which is an SL2Z modded by Z2. Very good. So that's what the I mean the modular group on this T2 is on the torus. Now let's look at some particular examples of these guys. Okay.
Sir.
Yeah. Yes.
So this group is the group which keeps the lattice invariant, right?
That's right. Yes.
Okay.
So, but it will act on the tau in some way, but it keeps the I mean keeps this I mean this structure the same basically. Yeah. This one, right? So that's the thing. So you want to keep the lattice structure the same. Okay, now let's look at some particular transformations where we transform alpha 1 alpha 2 to which is 1 1 and tau to 1 and tau plus 1. So what is happening? So if this is tau and this is 1, so this is going to be your tau I mean tau plus 1. As you can see, this is going to also I mean generate for you the same lattice. Okay. Now you see that even though the lattice stays the same, the modular modular parameters are not is not. So this has undergone I mean a transformation of tau goes to tau plus 1. So that's one. So this is going to be called the I mean T transformation, if you wish, the modular T transformation. So that's one. And let's look at another one where alpha 1 alpha 2 goes to which is 1 and tau goes to 1 plus tau and tau. So let's do this. So let's look at this. So this has gone to this is the same, but you have changed this guy to go here. Okay. So again, it spans the same thing. And now what has happened is that your tau has gone to tau by tau plus 1. Okay. So this is the U transformation, and then what you want to do. So that's what the U transformation is. So just a second. Yeah. Okay. Now it's actually more you see that instead of you can work with S, and S is tau goes to minus 1 over tau. Yeah, I mean, and operationally, this actually just exchanges, alpha 1, alpha 2 with minus alpha 2, alpha 1. Okay, so this again is a particular form of the SL to Z transformations that you have. As you can see that this guy, this would be, for example, if you're looking at, if you have a equal to, sorry, so the S transformation is just A equal to 0, B equal to -1, C equal to 1, and D equal to 0. And for example, the T transformation is A equal to 1, B equal to 1, C equal to 1, D equal to 0. No, sorry, not C equal to 1, D equal to 0, or the other way around. C equal to 0, D equal to 1. So these are the forms of the transformations that we have highlighted out here. And it's important to look at these guys. And what happens, we're not going to prove this, is that S and T actually turn out to be the generators of this particular modular group. You can also check these particular relations, and you can just plug them into the vectors and series. And I mean the matrix that I showed you, and you can just just multiply them, and you can find this out. Okay, very good. So these are the transformations. And what are we interested in? The thing that we are going to be most interested in this this part of our of our discussion is questions regarding the partition function. Okay, before doing that, before going there, are there any questions that you guys would like to ask?
Sir, can you
Yes.
go back to the previous slide?
Sure.
Slide before that.
Okay.
Yeah. So all these ABCD transformations leaves the lattice invariant, right?
Yeah.
So why are we just like basically what's so special about the Z2 that you mentioned, that alpha 1, alpha 2 going to minus alpha 1, minus alpha?
No, what I'm saying is that this particular thing,
yes,
something. Okay, so let's say, so if you have this, and if you have if you have something like minus A, minus B, minus C, minus D, both of these would be the same, right?
yeah, because they are leaving the same alpha 1, alpha 2.
Yeah, I mean the thing at the end of the day is that if you have something which is alpha 1, alpha 2, and if you have something which is minus alpha 1, alpha 2, these will be the same, right? I mean, so your beta in a sense is minus alpha 1, minus alpha 2. Then your A's and B's will, so that's like a trivial thing, right? So you want to mod out by this.
This Z2 action, which is applied on the SL2
Yeah.
comma Z,
Yeah.
is normally for exactly this minus A, minus B, minus C, minus D.
Yes.
But it doesn't change the alpha 1 and alpha 2. When like negative signs will simply cancel out and alpha 1 and alpha 2 remains the same. Basically, tau is not changing.
Yeah, so the tau will so what I'm trying to say is that the tau will not I mean you're right, the tau will not change, right?
Yes.
So the invariance of the group hence is not a full SL2Z,
SL2, yes.
but it's
But
an
instead mod
SL2Z
Z2.
modded by a Z2.
Yes.
This is just to do with the fact that it's, I mean, trivial that if you have something which is, I mean, alpha 1, alpha 1, alpha 2, and if you have something which is minus alpha 1 and minus alpha 2, things will not change, right? Yeah, you can also see that from the fact that when we defined I mean tau, there is a, you know, it's an alpha 1, I mean alpha 2 by alpha 1. So if you put two signs out here, things will not change, right?
Uh, I guess I mixed up a bit. Basically, I was saying, for example, if you want to go from alpha 1, alpha 2 to minus 1, minus alpha 2,
Mm-hmm.
the ABCD will be minus 1, 0, 0, minus 1.
That's right. That's right.
Not
Yes.
minus A, minus B. Like, it is not the, um,
Yeah.
like, going from
What I'm
alpha
trying to
1.
say is that the tau that you're going to get, okay, uh, tau which you're going to get by alpha 2 I mean by alpha 1,
Yes.
and if you have a I mean tau prime which is minus alpha 2 by minus alpha 1,
Yes,
these
sir.
actually are the
That will be
same, right?
same. Exactly, yes.
So it's not the full group. You need to mod out by a z2.
No, yeah.
That's I mean
Okay.
that's the thing. Yeah, I guess that's what I was trying to say.
Okay. Thanks.
Yeah, sure, absolutely. Oops. Any more questions?
So the T transformation has determinant 0, right?
Determinant 0? No.
A
No.
maybe
So
I'm
so
wrong.
a will be what? So I mean the t is t takes tau to tau plus 1, right? So
Yeah.
then a has to be equal to 1, b has to be equal to 1, c has to be equal to 0, and d
Okay,
has
D
to
is
be equal
1.
to
Right.
1.
Yeah.
So the determinant is always 1. So determinant for, I mean, all of these things will be equal to 1.
Yeah.
Okay. Any more quick questions? Oops. No. Let me just erase this. Sorry, just give me a sec. I'm just going to delete the whole thing. I don't want that. All right, very good. So if there are no more questions, let me try and move on. So what we want to do is we want to understand what the partition function is. So now remember, so this is something that you all are going to be pretty at home with. But what is a partition function? A partition function say statistical mechanics is a sum over all I mean all sorts of possible configurations, and you remember that you weigh all of these guys with this Boltzmann weight of I mean exponential minus beta h. In a field theory, this is something that you are again most probably familiar with. This is just a generating functional. And given the fact that a CFT, I mean, sorry, not a CFT, a field theory and a statistical mechanical system are actually related, when you are looking at a Euclidean CFT, and there you I mean compactify what your previous time direction was uh, to a circle of radius beta, then you can link up the two things. Remember, that's how you relate statistical systems to field theories. Very good. So what do we do for CFTs? For a CFT now, so what we will do is we will choose the real part of omega as being spatial, and the imaginary part of omega as a time direction. This is a slight change in notation from earlier, but remember the SS transformation will exchange them so it's not that much of a problem. So this is what we're going to do. We're going to take the real part of omega to be space and the imaginary part of omega as time. And now what do we have to do? We have to you have to do something where you have sort of identified the time, I mean time direction. So you want some closed loop, right? So let's try and understand this. Okay, so you want to go from this point to this point, you want to close the loop, if you wish. Now remember, if you were to go from something here to something here, the I mean this particular time translation will not land you up in, I mean, on the same T2. In order to do that, you also have to move this way a bit. Okay, so this is so you also have to, so in order to get a closed loop in time, not only do you have to move in time, but you also have to move in space. So you need to identify, so this is what is happening. So just a time translation by I mean tau2 is not going to land you up in the same torus. You also need to have a spatial translation, and hence a closed loop in time is going to be something which does this and this to you. Okay, so this motivates how you can write down a partition function. So what is that going to be? A partition function is going to be something which is, this particular translation in time. So that's the thing that I have written for you here. 2 pi's are a matter of convention, and so and into the I mean time translation operator. Remember, only this will not do. You also have to do something in space. So that is this thing in thing tau1 into the space translation operator, which is p, and you need to trace this over the whole Hilbert space H, and that is what you will have. So in a usual sort of field theory, I mean in a usual stat mix system, this used to be trace of e to the minus beta H, and this beta was the uh, so this turned out to be the identified I mean time direction. So this sort of translated into 2 pi tau h, there's a sign, but you cannot just do this one. Okay, so you can't just do this. You also have to have a, I mean, in order to close the loop, if you want to get back to the same system, you also have to have a spatial translation. So there's this extra piece that you need to add, which is this guy. Okay, so that's what you need to keep in mind. So that's what this was all about. As I said here, I mean, the Hamiltonian is the one that generates time translations, and P is the momentum which generates this spatial translations. And the trace is over all the states of the Hilbert space H. All right. Now you have written this down. This is what the partition function of, I mean, the partition function of the CFT is. We need to figure out what H and P are. Okay. So remember that if you are looking at the ground state, so if you are looking at the ground state energy, that's just I mean the 1-point function of T naught naught on, I mean, on the cylinder. Sorry, this is an exercise we did earlier, and you can come up with the fact that this is just minus C plus C bar by 24. This is the Schwarzian, right? So this is the piece that comes from the Schwarzian, and the fact that the translational invariance on the plane means that T plane is equal to 0. Right? If you don't remember this, just stop me. Is this okay? Okay, I guess it is. So E naught is this. So the Hamiltonian will be what? The Hamiltonian will be, I mean, del del T plus E naught. And if you translate this into the coordinates on the cylinder, this is just I mean omega plus del omega plus del omega bar, and E naught is C plus C bar with a sign in front of it. And this is the same as just L0 cylinder and L naught bar cylinder 0. I mean L naught cylinder and L naught bar cylinder. So these are the two things. And similarly, you can write down what the momentum operator is, and you will find that it's L naught minus L naught bar. So what you do is that you write down Z. Z is now trace of 2 pi tau 2, L naught plus L naught bars. These are on the cylinder, remember, and minus plus or 2 pi I tau 1 into L naught cylinder minus L naught bar cylinder. Now remember that the modes on the cylinder will be moved around a little bit. So this is just, if you just wrote it in terms of, tau and tau bar, this is 2 pi I tau into L naught cylinder and 2 pi I tau bar into L naught bar cylinder. Remember that these L naught and L naught bars are related to the things on the plane. Sorry, where did I write that? By the following relation. I wrote this a lot earlier. Not even here, somewhere here. Yes. So remember that L naught on this cylinder is related to L naught on the plane by the central charge factor. So going back, what we find is the following. Going back, we find that the Z is going to be given by this form where you have written Q as e to the 2 pi I tau. So it's Q to the L naught minus C over 24, Q bar to the L naught bar minus C over 24. Okay. Notice that if you were to translate these, there is a crucial, there is an extra sign out here which you need to keep in mind. Now, let me just drive home this particular message once more to you. Is SL2Z by Z2 transformations of this modular parameter tau, they do not change the thing that you're on. So the torus is unchanged by it. So the CFT will also be unchanged by it. As a result, the partition function will also have to be invariant under it. Okay. So this is going to be one of the major defining factors of what we are going to be doing in this in these few lectures, that the partition function is going to be invariant by the action of this particular modular group. For example, one of the things which is going to be important is that, remember, what we were doing before is that we had these left movers or the chiral fields and the right movers or these anti-chiral fields, and we were saying that you just do this and the rest of it you can just plug in. So that's not a problem at all, and we didn't really we didn't have any way of imposing anything, in the sense that how chiral and anti-chiral fields going to fit together. We were just saying that there's this sort of factorization, and you just do this, and the other piece is just an identical thing. Now what is going to happen out here is that there is, since you are on a sort of on this T2, there is going to be some very strong ways, constraints in which chiral and anti-chiral fields can actually combine with each other. We will see this as we go forward a bit, and remember that on the plane these things were not there. Okay, so this is what we have learned. So what we have learned is that when we are looking at this CFT, and so one of the reasons why we were trying to look at all of this was because we had this example of string theory where it's necessary to have things, I mean have you need to look beyond tree amplitudes, and you need to look at things where you have loop amplitudes as well. That naturally brings us to sort of higher genus Riemann surfaces, and you need to look at CFTs on these higher genus Riemann surfaces in order to, if you wish, look at the consistency of string theory. You can also, I mean, obviously look at these things for various metals, I mean, various other applications. And one of the things that you need, I mean, that this does for you, as we saw near the end of the class, is it generates for you this partition function in a very nice way. So you would be able to now demand this modular invariance of the partition function to actually get, and I mean, lots of interesting things out of the theory. We will see this, and one of the sort of very nice things to happen out of it is, by doing this, you can actually relate the low energy states of the theory with the extreme high energy states of the theory, and thereby you can actually get an understanding of what the number of states in the theory would be, and what the entropy of this system would be like. We will try and work those out a little bit in the next class, and well, I don't know if it's in the next class, but before we end the course, we will actually work some of those things out. Okay, so I'm going to stop today, because I think this is a nice point to stop. Of course, if there are any questions, I'm happy to try and address them. Okay. Let me stop sharing my screen.
So I have a question.
Yeah, yes, please.
So how many how many generators should the group SL2Z modded by Z2 should have?
How many generators? So since we are modding out by this discrete group, the number of generators, so you will see that this is actually generated by SNT itself.
Yes, that's what I was asking. So
Yes.
S, T, U are independent, or only S or T are independent?
I mean
only
SNT actually. So you
Ah.
would be able to get, so I mean, as I wrote in one of these things here, you can write down
Yes, there is a
u in terms of these. So okay, so there is, I mean, u can be written in terms of yeah, I mean SNT.
Yes. So
Yeah.
I mean, I was trying to connect with counting the independent parameters. So SL2Z itself have 4 parameters.
That's right.
All are integers. So there is the determinant condition.
That
So
brings it down. Yeah.
So
by 1.
what is the another constraint?
What is the other constraint?
I mean, modding out by Z2, does it give any constraint or?
That's a good question, actually. It's a discrete subgroup. I mean, since this can be generated by SNT, the answer has to be that the number has to be down by 1.
I mean 2. Yeah.
So the number has to be 2, right? So these are the only 2 independent ones. Yeah, so the answer should be that it's down by 1, but I don't have an immediate proof for you, actually.
Yeah. Okay.
So that's yeah. So maybe we should try and look at this ones. So there are these other things as well, right? Then S squared is equal to 1, and ST cube equal to 1 as well.
Yes. Yeah.
So these are sort of further constraints, if you wish.
No, these are properties.
These are well. These are just, I mean, the fact that probably No, the fact that STU and ST and U are not independent, that makes it clear that these. I mean, the
Yes.
number has to be less.
Yes.
And the fact that these they square up to 1 and st cube equal to st cube equal to 1 is sort of is basically the fact that you're going to deal with these particular matrices. So that I think is fine. That's not an extra thing on S and T, but the fact that you can relate, you can write this, one in terms of the other means that you can, there are only two independent ones.
I mean, yeah, that's fine
Yeah.
from those explicit construction, but I
You
was
are
thinking about
saying that if you have a discrete subgroup, and
yes,
if you
so
are going to mod something out by a discrete subgroup, what
so
is the number of
that
generators?
effectively gives C greater than equal to 0. So that's the condition. But is it a constant?
I would think it is, right? Because otherwise you would have had 3, right?
Yeah, but it's an, I mean, I don't understand this.
Yeah, so this is going to be related. So if you if you have a group G,
Mm.
and if there is a subgroup H, and if
Yes.
you're looking at the coset of G mod H, then
Mm.
the generators of the coset G mod H, if that's, if that again is a group, is the number of generators of G minus the number of generators of H. In this case, it would have been the number of generators of G were 3, and it seems that so the Z2, the generator of Z2 should, the number should be 1, I guess, right? And
Uh, yeah.
hence the number of G mod H should be equal to 2.
Mm. Okay.
Yeah, I think that's what it is. But
Yes.
yeah, I can have a look at this and try and say this thing a little more clearly next time around.
Okay. So that's fine. That was from definition, but yeah, I can't explicitly see that. Yeah.
Yeah, so I don't have something on the top of my head which will just give you this, but yeah, I think the number has to go down by, needs to go down by 1,
So
because yes, yeah,
SL2Z is a discrete group, and in
yes,
discrete groups, number of generators actually doesn't follow the same additivity rules as the rank. Like basically, SL2R would have had the like three rank, like 3 number of generators, and then even if you modulo it out by Z2, it will remain 3 because it's discrete group that you're modulate with. But in the case of SL2Z, it doesn't actually have that same additivity. It does have some sub additivity like
okay,
inequalities,
okay,
but not proper additivities.
okay.
And the T is
Mhm.
a like T is a rank 2 operation. Rank 2, or yes, like if you repeat it, T square will be identity, right?
That's right. The T
Yeah.
squared will
No.
not be
A
T to the
square.
power
square
4
will
or
not
T
be
square.
identity. S squared will be identity,
Yeah,
right?
sorry. Yes, yes.
Yeah,
S
yeah,
square will be identity, right?
yes, yes.
So S itself doesn't actually have a like one rank itself, because normally rank is count in these discrete groups. Ranks are counted by
Uh-huh.
the Z to the power, right?
Yeah, yeah.
Yeah,
Yeah.
it turns out ki T is the only one which is actually generating the rank, and the S is actually changing the parameters for like different combinations.
Okay. Okay.
So T separately is actually incrementing a different parameter, S into T incrementing a different parameter,
Uh-huh.
and T into S is incrementing a different parameter, something like that. So SL2Z will have three parameters. That's what we want, right?
That's right. Yeah.
Is incrementing one of them, and S into T will be incrementing the other one
Yeah,
in
true.
some
True. Yes.
specific representation,
Yes.
and then T into S will be representing some other.
Or ST squared, I guess. I
Yeah,
mean,
something
yeah,
like that.
yeah,
I
yeah.
like ST square. Yeah, something like that. Yes.
Yeah. I mean, ST squared will, I mean, since ST cube is equal to 1, so you'll have something with, I mean, ST squared, I guess.
Yeah. And in different representations, they will change a bit.
Yes. No, if you look at the, yeah. Yeah, this is something that I need to have a look at actually. This it is a discrete group, which is, it seems to be, yeah, it's, yeah, but you can also, well, okay, let me have a look at this, and I mean actually get back to you guys on this a bit, okay?
Okay.
Because yeah, it's a little confusing for a few things, but let me do that. All right.